In this video, we'll be looking at the multiple choice questions from the Edexcel Chemistry paper or Chemistry Unit 1, International Advanced Level for the year 2016. Question 1. We have 8 parts per million of oxygen dissolved in water, and we are expected to express it in terms of the amount of oxygen dissolved in 1 kilogram of water. Right, so let's write out the expression first in terms of parts per million. Since it's 8 parts per million, we can say that it's also 8 grams of oxygen per every million grams of water. That is how we get parts per million, right? And then our aim is to convert or to express the denominator in terms of 1 kilogram. So leaving the numerator as it is, 1 million grams will be 1000 kilograms of water. And then if we want to express the bottom, or we want to change the bottom to 1 kilogram, which is our aim, we have to divide 1000 by 1000. And if we do that to the denominator, we have to do the same thing to the numerator. So 8 divided by 1000. And then we will end up with 8 over 1000 grams of O2 over 1 kilogram of water. Right, so we have achieved our aim of expressing the denominator as per kilogram. So we have 8 over 1000 grams of oxygen per kilogram of water. In standard form, the answer is B. Number 2, calculate the total number of atoms in 8.5 grams of dichloromethane. So first of all, we can try to find out the moles of dichloroethane. That will be the mass over the molar mass, 85, right, even over here. So we have 0.1 mole of dichloroethane. And how about the moles of atoms? Right, we have to observe that there are, for every one molecule, there are 5 atoms. Right, 1 carbon, 2 hydrogen, and 2 chlorine atoms. So every one molecule, we have 5 atoms. So if we have 0.1 mole, we have 0.1 mole multiplied by 5 atoms. 5 times the number of atoms, 0.5 moles of atoms. And then the number of atoms is 0.5 moles. Right. A mole is essentially 6 times 10 to the power of 23. So 0.5 times 6 times 10 to the power of 23. This is the number of atoms. Number 3, hydrogen is mixed with chlorine and the gases react based on the equation below. Right, what is the total volume of gases present at the end? So we will try to have a table that keeps track of all the volumes of gases. We have hydrogen, chlorine, and then our products will be hydrogen chloride. Now, initial, let's find the volume. Initially, we have 50 cubic centimeters of hydrogen. Chlorine will be 25. There isn't any hydrogen chloride formed yet, so the initial volume is 0. The change in the volumes of gases. Now, observe that the ratio that chlorine and hydrogen reacts will be 1:1. and then we have 25 cubic centimeter of chlorine, 50 for hydrogen. So we must realize that this is in excess. We have excess hydrogen. We can also say that the chlorine gas is the limiting amount, right? Because we only require 25 to react with 25. We have a lot more hydrogen than we require. So chlorine is the limiting amount. We will have to use this amount to figure out the changes. So all of the chlorine will be reacted. So I subtract 25. If 25 cubic centimeter of chlorine is used up, it will also use up 25 cubic centimeter of hydrogen, because like we said, ratio is 1:1. If 25 cubic centimeter of chlorine is used up, it will produce twice the amount of hydrogen chloride, right? Because now the ratio is 1:2. So we will be producing 50 cubic centimeter of HCl, right? Producing, the change will be positive. Let's find out the amount of gases in the end. Hydrogen, we had 50, we used up 25, so in the end we have 25 left over. Chlorine, no surprises, we use up everything, so 0 at the end. And hydrogen chloride, we form 50. So the total amount is 25 and 50, right? That will give us 75 in total. Answer is A. Number 4, sodium hydrogen carbonate decomposes. What is the maximum volume of carbon dioxide from a quarter mole of sodium hydrogen carbonate? So essentially this is the amount that will get us started for our calculation. 0.25 moles of sodium hydrogen carbonate. So that is for here. Right, 0.25 moles. Our target is to find out the amount of carbon dioxide. So let's compare the ratio. For every 2 moles of sodium hydrogen carbonate, we have 1 mole of carbon dioxide. So if we had 0.25, carbon dioxide will be 0.25 divided by 2. We will be expected to produce 0.125 moles of carbon dioxide. And then we are required to find out the volume of the carbon dioxide. So volume of carbon dioxide is the number of moles that we expect multiplied by 24. Alright, because for every 1 mole is 24 dm cube. If you have 0.125 moles, is 0.125 multiplied by 24. That means we will be expecting the maximum volume to be 3 dm cube. Number 5, we are mixing an acid, hydrochloric acid, with alkali, sodium hydroxide, and we are measuring the change in the temperature. So what we have in the solution will be 50 cubic centimeter of the acid and 50 cubic centimeter of the alkali. Right, so what is the total mass of the solution? First of all, the mass of the solution, the total volume of the solution is 100 cubic centimeter. Right, 50 from the acid, 50 from the alkali. To find out the mass of the solution, we have to use the information that 1 cubic centimeter weighs 1 gram. That is the density. So 100 cubic centimeter will be, it means that the solution has a mass of 100 grams. So let's get rid of this. That means that during the heat of neutralization, the energy transferred is used to heat up 100 grams of the solution. So energy transferred based on this equation, mass of the solution 100 grams multiplied by the heat capacity given to be 4.2. The change in the temperature is from here 12 degrees. This is the energy transferred. What is the enthalpy change of the reaction in kilojoules per mole? So enthalpy change will be equals to the energy transferred divided by the moles of the limiting reactant. So let's look at the number of moles that are involved here. Each solution contains 0.1 moles of solute, so it means that we use 0.1 moles of sodium hydroxide and 0.1 moles of acid. Right. In this case, either of them can be used as a limiting reactant. Neither of them is in excess. Right. So we could use, we will be putting 0.1 moles as our denominator here, the moles of the limiting reactant. If the question has changed such that it was 0.05 moles, for example, for sulfuric hydrochloric acid, then we realize that it is actually the hydrochloric acid that is in a limiting reactant. We have to divide the energy transferred over 0.05 moles, right? Based it on the moles of your limiting reactant. However, for this question, both were 0.1 moles, so it doesn't matter which numbers we use in the numerator. The energy transferred 100 multiplied by 4.2 multiplied by 12. Right, it's almost done. We have to take note of that the energy transferred was expressed in joules, and they want the expression in kilojoules, so we have to take this number divided by another 1000. We have to put 1000 in the denominator because we need to convert joules to kilojoules. And then finally, this is a neutralization reaction. It is exothermic, so we have to be mindful to indicate the negative sign to the overall change. Right, so this is the enthalpy change of the reaction. It corresponds to option C. Number 6, in the synthesis of ammonia, we use 56 grams of nitrogen and we obtain 6 grams of ammonia. This is the products, right? What is the percentage yield? Let us find out the moles of nitrogen that was involved in the reaction. Moles will be mass over the molar mass, referring to the periodic table, is 14 times 2. So we had 2 moles of nitrogen involved. If we were to use 2 moles of nitrogen, we will expect 4 moles of ammonia. Ratio 2 is to, or ratio 1 is to 2. So expected moles of ammonia is actually twice the amount, 4 moles. The expected mass, that means 100% yield, will be 4 moles multiplied by the MR of ammonia. 14 plus 3, 17. So if it was 100% yield, we will expect we will actually be getting 68 grams. Right, but we didn't get this in the end. We only got 6 grams. So the percentage yield is actually our actual mass obtained, 6 grams, over the expected mass that we're supposed to have, multiplied by 100%. That gives us about 8.82%. So answer is B. Number 7, which of the following has the smallest ionic radius? Now, let's start off with the number of electrons they have. Initially, for the atoms, right, you can refer to the periodic table, 8, 9, 11, and 12, respectively. These are the atoms, right? And then for the ions, when they lose or gain electrons, they actually all ended up with 10 electrons. So they have the same number of electrons. In other words, the electronic configuration for them are the same. So what affects their radius then? That will depend on the number of protons in the nucleus, right? The larger the number of protons, the stronger the attraction force between the nucleus and the outer electrons. The stronger the attraction force, they will be pulled closer inwards towards the center. That means the radius will be smaller. So we have to look at which one contains the largest number of protons. That will be magnesium, right? Magnesium has the largest number of protons. It will pull the electrons closer, so the radius of the ions would end up to be the smallest. Number 8, magnesium chloride crystals prepared using magnesium oxide and hydrochloric acid. We get salt and water. So ionic equation. Now the thing about ionic equation is, if you see state symbols like solid, liquid, or gases, we essentially do not change the formula, right? But if you see compounds with aqueous states, right, we will split them into their ions. So let's use this as an example. Hydrochloric acid, right, it is aqueous, so we will split it into its ions. Hydrogen ions, there are 2 of them because it's 2HCl. Chloride ions, 2 of them, right? This is a hydrochloric acid being splitted into its ions. Magnesium oxide is solid, so we do not make any changes to the compound. We will just write it out as it is. And going over to the other side, magnesium chloride, aqueous. Since it's aqueous, we split it into its ions, magnesium ions and chloride ions. Right? There are 2 chloride ions. And then finally, water is liquid. We do not make any changes to its formula. Right. So now the aqueous are all separated, the ions. We will have to observe and cancel the ions that appear on both sides of the equation. Right. We see that chlorides appear on both sides. We can cancel them out. Right. That's essentially what we can do. So what we are left with will be the ionic equation that corresponds to D. Alright, B, the amount of hydrochloric used was 0.1 moles. Which of the following contains this amount of hydrogen chloride, or of hydrochloric acid. So we are given volume. For the 4 options, we are given volume and we are given the concentration. So the simple equation is number of moles is equals to the volume multiplied by concentration, right? But then you have to be mindful to change the volumes to dm cube, because right, the concentration is expressed per dm cube. So going down the list, for A, we have 100 over 1000, because we have to convert it to dm cube, multiply by 0.1. Right, that will give us 0.01 moles. Right, that doesn't correspond to the 0.1 mole that we want. For B, same approach, volume multiplied by the concentration. Again, we get 0.01 moles. C, volume multiplied by concentration, 0.01 moles again. So it should be D. Let's check. 20 over 1000 multiplied by 5. That will give us the 0.1 moles, which is what we want. Part C, an excess of magnesium oxide was reacted. Which of the following is the smallest mass which will produce an excess? So let's quickly write out the equation again. Magnesium oxide and hydrochloric acid. So we have the information that there was 0.1 moles of hydrochloric acid. What is the number of moles of magnesium oxide? Notice that the ratio they react is 2 moles of acid to 1 mole of magnesium oxide. So 0.1 moles of acid will require 0.05 moles of magnesium oxide, half the number of moles. To find out the mass, we will take the moles multiplied by the molar mass given over here. That will give us 2.015 grams. So which of the following will provide an excess? Which of the options will give us an excess? All right. If we use 1.5, we will not have enough, so it will not be an excess. The first time we will get an excess is if we were to use 2.5 grams. Right, we will be provided, we only need 2.015. If we were to add 2.5, we will start to have an excess. So this is the smallest mass that will give us an excess. Part D, what is the first step in obtaining the pure crystals after we carried out part C? Okay, now we have added excess of magnesium oxide. That means in the mixture we have our excess magnesium oxide, which is a solid, together with our magnesium chloride solution. So before we can crystallize out the salt, we will need to remove the excess magnesium oxide. And how do we remove a solid particles from a solution? We will need to filter the mixture. Right, once we filter the mixture, if you were to carry on the discussion, if you filter the mixture using a filter paper, the funnel, we will have the solution of magnesium chloride, and then we can carry on doing our crystallization procedures. Part E, use the data below to calculate the number of moles of water of crystallization, right, in hydrated magnesium chloride. So hydrated magnesium chloride, the formula can be expressed in terms of MgCl2, water of crystallization, with an unknown number of water molecules. Right, we don't know how many water molecules there are for every 1 unit of magnesium chloride, so let's just assign it to be X. So what is the MR? MR will be, for magnesium chloride, they have given us 95.1. The MR for the water molecules will be the number of water molecules, which is X, multiplied by water, 1 or 2 plus 16, so 18X. Right, this is for the MgCl, and this is for the water molecule. This is the total MR of the hydrated. And we are given the information that the hydrated MR will be 203.1. So we have an equation with an unknown X here. Arranging the equation, 203.1 subtract 95.1, 18X will be equals to 108, and then X is 108 divided by 18. There are 6 water molecules attached per unit of MgCl2. Number 9. What is the equation of the lattice energy of magnesium chloride? So you have to be familiar with the definition of lattice energy. Is where 1 mole of the solid ionic compound formed from the gaseous ions. The ions must be in gaseous form, and the amount of solid ion compound form will be 1 mole. So in terms of magnesium chloride, we will have 1 mole of magnesium chloride solid form, and we need to have its constituents ions. Magnesium ion in a gaseous form, chloride should be Cl2, and then chloride ions, 2 of them in their gaseous form. Right, gaseous ions forming solid ionic compound. So that corresponds to C. Number 10, empirical formula. So we are given the data for carbon, hydrogen, and oxygen. So let's create a table. So as per usual, the convenient way to look at it is we have a 100-gram sample. So the mass, the respective masses will be 54.5 grams, hydrogen 9.1 grams, oxygen 36.4 grams. And then we have to convert it into the moles. The moles we will divide by their respective relative atomic masses. Carbon is 12, hydrogen 1, oxygen 16. And dividing by that, we have 4.5, 417. Right, you will be using your calculator for this. 9.1, 2.275. Right, these are not nice whole numbers yet at the first stage. So let us try dividing by the smallest number among them. In this case is 2.275. So let's divide throughout by 2.275. then once we do that, it becomes 2, 4, and 1, right? Nice whole numbers. So C, 2, H, 4, O. Option B. Right, how do we name this hydrocarbon? Let us find out the longest chain. Right, longest chain apparently is here, this C shape. So 1, 2, 3, 4, 5, 6, 7. 7 carbon chain, that will be heptane. Then let's look at the branches. At carbon number 4, we have a methyl branch, 1 carbon branch, and then at carbon number 4 we also have another branch, the ethyl branch. So we have heptane, 4 methyl, right, and then 4 ethyl. So D is the answer. Which of the following shows geometric isomerism? Let us try to draw the structures for the 4 options. Propene, alright, and then if you observe the double bonds, the propene cannot have the geometrical isomers because the carbon, this carbon has 2 identical groups. That will not allow it to give us geometric isomers. There will be no cis trans. But1 in. Okay, but1 means the double bond is at the first carbon. Right, again, by now we should realize that it cannot have geometrical isomers also, because if you look at this carbon, same thing, it has 2 identical groups. So no geometrical isomers for but1 in. But2 in, butene, and number 2 means that the double bond is located at the second carbon. Right, and then focusing on the double bonds, this one, there is a possibility of it having geometrical isomers. Right, this carbon has a hydrogen group and a CH3 group, no identical groups. So this one is the one that has geometrical isomers. Right, for that matter, again, this one will be our cis isomer. The trans version will be where the groups are diagonally opposite each other. This is also but2 in, but this is the trans isomer. Right, let's see why D is incorrect, just to finish up the options. But2 in, this is but2 in, and then there are branches, 2, 3 dimethyl. So carbon number 2 will have a methyl group, carbon number 3 have a methyl group, so can't have geometrical isomers. Right, the carbons have identical groups attached to them. Number 13, which of the following is a reforming reaction? So reforming, one way to look at it is either from a chain of alkanes, it will either form a ring or it will form more branches. Okay, so D will be answer, right? It actually becomes more branched. That's a reforming. The rest, apparently they are being broken down into smaller molecules, so the rest can be actually described as cracking. In the reaction of methane with chlorine, ultraviolet light causes, okay, so this is the free radical substitution for chlorine. Ultraviolet light will break the bonds. One of the electron will go to one chlorine and the other electron will go to the other chlorine, so that we have two free radicals. So there is an equal splitting of electrons, or equal sharing of electrons once they go their separate way. So it's a homolytic reaction or homolytic fission. Homolytic means they share equally. If one chlorine takes both electrons, then it will be heterolytic. Alright, but because the two electrons are shared equally, it is homolytic. And the homolytic fission is between the chlorine bonds to form the chlorine radicals. Number 15, forming of chloromethane, and we are searching for the propagation step, possible propagation step. So for chloromethane, there are two propagation steps that we have to be aware of: the methane and the chlorine radical, forming a methyl radical and hydrogen chloride. And the methyl radical can also react with a chlorine molecule, forming chloromethane and a chlorine radical. Right, so propagation steps, if you notice, propagation step, we consume one radical and we produce another radical. And then the options here, right, we can see that B, right, actually corresponds to one of the possible propagation steps. Empirical formula of polyethene, right, the monomer of polyethene is the ethene molecule, CH2. The polymer, after it polymerizes, the structures can be drawn in this manner. The double bond is broken and single bond, right, and being a large number. So empirical formula, well, C2H4, if we were to simplify into the simplest ratio, the empirical formula is CH2. Option B.